Okay, this is part 2 of 2 parts. Inductors RL part 2, review lecture 7-2B. If you have not yet viewed part 1, please go do so. It's called L7-2A, Inductors RL part 1. If you don't do that, you might not know what's going on. You remember the capacitor. When we charged up a capacitor, we wound up with something like this. The circuit looked like this. We flipped the switch to A to cut in the battery. And of course, the capacitor was initially uncharged. And of course, once we did this, the charge on the capacitor will increase according to Q equals C times the EMF times the quantity 1 minus the x1 minus T over RC. Of course, the final Q, the final charge, is just C times E. Tau C is RC, which is the capacitive time constant of the circuit. During the charging, the current and voltage would be I equals dQ dt, and that equals EMF divided by R times the exponent minus T over RC. And VC, which is voltage across the capacitor, just Q over C, that equals the EMF times the quantity 1 minus the exponent minus T over RC. And this rising curve like this. And it turns out that an RL circuit pretty much works the same way. The only difference in here, this will be a different formula. You'll have an L instead of a C. So some of the formulas will change, but you still have this part. And it still looks like that. And you still have this part. The exponent is still there. Okay, so this is for Physics 222 students, those who have calculus. If you do not have calculus, please skip to the solutions on the next page. Okay, so we're going to take the circuit here, and we've cut this battery in, and this is a charging or building up circuit, RL circuit. So we're going to go and break this down. We're going to apply Kirchhoff's loop rule all the way around. So we go from X to Y. We're going in the direction of the current, and that will be minus, we're down the waterfall, minus I times R. Then we go through the inductor from Y to Z. Now, the inductor is trying to fight the change. So it's going to develop an EMF opposing the change. And the EMF is going to be, in that case, minus L di dt. Minus sign comes from the fact that it's trying to fight the change. It's Lenz's law. Then we go through the battery. We're going from the negative to the positive terminals. So it's going to increase it by positive E. We put this all together. Minus IR minus L di dt plus E equals 0. We can reduce this a little bit, we end up with L di dt plus IR equals E. This is a differential equation, and we can solve this to an algebraic expression, and that will be the next slide. That's for both physics, calculus-based and non-calculus-based. Now we've done all this. We switch to A, we cut in the battery, and we do the solution. Okay, we find that the current will rise to an equilibrium value of E over R according to I equals E over R times this quantity, 1 minus the exponent minus T over tau L. Now, do you remember this? This part especially should look familiar to you. The only difference in this part was that we had tau C here instead of tau L. This looked a little different, but the formula pretty much looks the same. It's the same format. And look at, here's the plot of this. It looks like the same one for the RC circuit. So the inductive time constant is a little different. Instead of RC, it is tau L equals L over R. So initially, an inductor acts like an open switch opposing changes in the current. And of course, we wind up with initially the current equals 0. A long time later, it gives up and acts like a shorter ordinary connecting wire. Then I infinity is just the EMF of the battery divided by the resistance in the circuit. You can kind of imagine a stationary paddle wheel, and you dip it into a flow of water. Okay, and initially it doesn't want to go anywhere because it has inertia. So it resists the flow and blocks the flow. But eventually it gives up and it starts spinning. And eventually it's spinning along with the current and no longer obstructs the flow and acts as if it's not present. So the potential across the inductor terminal versus time is EL equals minus the EMF of the battery times the exponent minus T over tau L. This is for physics, calculus-based students, Physics 222 students. If you are algebra-based, please skip ahead one slide to the solutions. Okay, so we're going to determine the rate of current change. I equals E over R times the quantity 1 minus the exponent minus T over tau L. Do a little bit of algebra on it. And we say that I equals E over R minus E over R times the exponent minus R over L times T. We want to take the derivative of this to find the time rate of change of the current. And of course, this will just be 0. Take the derivative of E over R. It's constant. It's going to be 0. And then we can do the rest of this. It becomes minus the quantity minus R over L times E over R times the exponent minus R over L times T. We can simplify this a little bit. We can say di dt equals E over L times the exponent minus R over L times T. Now, this is the time rate of change of the current through the circuit. We can plug this in and use it to determine an expression for E across the inductor. We know that the EL equals minus L di dt, and EL then we can plug in for di dt. EL equal minus L times E over L times the exponent minus R over L times T. And then we can do a little bit of simplification. EL equals minus E times the exponent minus R over L times T. Now, of course, this is just the time constant, or one over the time constant. So EL is then minus the E, that's the EMF of the battery, times the exponent of minus T over tau L. And notice that the EL at time t equals 0 is just E of the battery, which we just said it's actually minus E, but magnitude is just E. And EL at infinity is 0 at times t equals 0. Since this is for both calculus and non-calculus physics students, so at time t equals 0, I equals E over R times 1 minus the exponent of minus T over tau L, and we're going to substitute t equals 0. When we do that, we find that the initial current is 0. So the inductor acts like an open switch. E across the inductor initially, it's just going to be plugging in 0 for time, and this becomes minus E, so it's minus the EMF of the battery. So the voltage across the resistor at time t equals 0 is 0, because there's no current in the circuit at that instant. So that's right here. T equals infinity, which is way out here somewhere. Okay, I equals E over R times 1 minus the exponent of minus T over tau L. And of course, now we're going to plug t equal infinity in here. And of course, when you do that, you end up with 0. And when you reduce it a little bit, you wind up with I at infinity equals just E over R. So the final current is just E over R, where E is the battery and R is the resistance of the circuit. So the inductor acts like a wire short circuit. It acts like it's not even there. Because it's given up the fight, it's no longer fighting any change, because the change has stopped too. So EL at infinity is just minus E times the exponent of minus T over tau L, or minus E times the exponent of minus infinity over tau L, which equals 0. The voltage across the resistor is the EMF across the battery. Okay, so remember this we did with this for capacitors, RL circuits, and time constants. You're going to notice something familiar here. First of all, this equation looks a lot like the one for the RC circuit. We had this term in there, and then a constant out front. And we have this T over tau. Okay, so all we're doing now is we have tau L instead of tau C, and we have a different constant out in front. But we're just going to evaluate this part of it right here. And we're going to do it in terms of time constant. So after one time constant, we end up with 1 minus the exponent of minus 1 times this. And 1 minus the exponent of minus 1 is 0.632. That should look familiar. On the other hand, EL equals minus E times the exponent of minus T over tau L. And we plug in that for 1. We end up with 0.368 times E. So I is 0.632 times the final value, so you're 63% of the way, 63.2% of the way to your final value for the current. For the EMF across the inductor, you only have 36.8% of what you originally started with. The minus sign just means it's opposing it. Okay, after two time constants, you're 86.5% of the way to the final current value, and you only have 13.5% of what was originally the EMF across the inductor. These should sound familiar. If you go back and look for the ones for the capacitor, you'll wind up with these same numbers because this is the same format. At the 3 time constant, you're 95% of the way to your final equilibrium value for the current. You only have 4.98% of the original EMF across the inductor remaining. At the 4 time constant, you're 98.2% of the way to your final equilibrium value for the current, and you have 1.83% of the EMF across the inductor remaining. At the 5 time constant, you're essentially all the way there. You're 99.3% of the way to the final current. You have less than 1% of the EMF across the inductor, the original EMF. So it's down to 0.674% of the original EMF. These numbers here are the same values as were for a charging capacitor. Because it has the same exponential time dependency, these two equations look exactly like, or very much like, the RC equations. So they'll behave alike. Okay, so here's what happens when you have an RL circuit and you're discharging it. After the battery's been connected for a very long time to this RL circuit, and it's established equilibrium, we're going to cut the battery out and we're going to move the switch from A to B, and that will short this RL circuit out. So now we're going to ask the current to drop to 0 in a very quick time. And of course, the inductor will fight this tooth and nail. So the inductor will act like a decaying battery as it resists the change imposed upon it by switching the battery out. And this is like what happens when you discharge the capacitor. It's the same sort of thing. The differential equation is L di dt plus IR equals 0. Now, don't be too worried about this. I'm not going to expect anybody at this level to understand differential equations. But if you're seeing it or we'll see it later, well, that's fine. Doesn't hurt anything. Education is education. Solution of this for everybody is I equals I naught times the exponent minus T over tau L. I naught, of course, is just E over R. That is the original current. That's this current here. That'll be EMF of the battery divided by the resistance of the circuit. And after a very long time, this will go to 0. The current will go to 0 too. So it drops off as a decaying exponential. And there's the decaying exponential right there. Now, there is sometimes a very large current present when switching out any large inductances, anything with a motor in it, such as a pump, an air conditioner, anything with a compressor, anything with a refrigerator, and as I say, air conditioning, any of these have large motors in them, large inductances, and they turn on and off repeatedly during the day. This can generate large and dangerous arcs and surges in the lines. Anything connected to these can be being damaged by these surges. So you have to take this into account for safety. So here's a tip for you. Never connect sensitive equipment such as computers, microwaves, or TVs, or your cell phone with its charger on the same circuit as your refrigerator, air conditioner, or anything with a pump. Surges from these motors can destroy your sensitive electronics. Now, your surge protectors will protect you to a certain extent, but they aren't perfect, and eventually they wear out. And the cheaper ones don't even tell you that they're no longer protecting your equipment. So I would strongly suggest that, if at all possible, avoid plugging anything sensitive into the same circuit as your refrigerator or anything that has a motor in it. So that's a good tip there. Okay, so here's an example. Here's an RL circuit, current during transition. Solenoid has an inductance of 53 millihenries and its own internal resistance of 0.37 ohms. Now, we can treat the solenoid just like any RL circuit. Even though we're talking about the internal resistance, it doesn't make any difference. If the solenoid is connected to a battery, how long will it take the current to reach half of its equilibrium value? Now, this is a real solenoid, but we're considering it small with a non-zero internal resistance. We're going to treat it like an RL circuit. The physics of this is a charging RL circuit. In other words, it's building up current. And the knowns of resistance is 0.37 ohms, and we want to convert the inductance to SI units, 0.053 henries. And we want to find out the time it takes to reach 1/2 of the equilibrium value for current. So I equals 1/2 E over R. So this would be the final current. So it's a charging inductor. It's building up. So I equals E over R times the quantity 1 minus the exponent minus T over tau L. And tau L is just a time constant of L over R. We have I equals 0.5 I infinity, and of course I infinity is E over R. So it'll be 1/2 E over R. So I equals 1/2 E over R, and the I at any time is just E over R times this quantity, 1 minus the exponent minus T over tau L. Now what we're going to do is we're going to solve this in terms of time. So we take, I will spare you this. Okay, you should be able to do these steps yourself and get to this step without any kind of trouble. If you have any kind of trouble with this, there's reviews in the back of most books that tell you how to handle things like this. Make sure you review that because you're going to need it for tests and lab. Okay, so T equals minus L over R times the natural log of 1/2, or we can say that is L over R times the natural log of 2. At this point, we're ready to plug in our numbers. So we know our T equals, the inductance is 0.053 Henry. We're going to divide it by a resistance of 0.37 ohms, take the natural log of 2. It is 0.10 seconds. So tau L is L over R. We'll get the time constant, and it is 0.053 henries divided by 0.37 ohms. Tau L equals 0.14 seconds, which is slightly greater than T of 0.10 seconds. The time to reach I equals 1/2 the final value, which is T, is slightly less than one time constant, which is the time it takes to reach 36.8% of the final value. So, and remember, this is decreasing. So T is going to be less than TL, and that's expected. Okay, here's another example. Energy stored in a magnetic field. A coil has an inductance of 53, it's the same coil, 53 millihenries and a resistance of 0.35 ohms. We're going to apply 12-volt EMF across the coil. How much energy is stored in the magnetic field if the current is built up to its equilibrium value? After how many time constants will half this equilibrium energy be stored in the magnetic field? So this is a real inductor, and it's a building up circuit, so it acts like a charging RL circuit. We write down our knowns. R equals 0.35 ohms, L equals 53 millihenries. Convert that right to SI, 0.053 henries. EMF is 12 volts. We need to know UB at an infinity and how many time constants it's going to take. So UB equals 1/2 LI squared. I at infinity equals E over R. And we also know that I equals E over R times the quantity 1 minus X1 minus T over tau L, and we're going to need this in the next page. At infinity, for T equals infinity, UB equals 1/2 LI squared. At this point, we just have to plug in what we have. It's 1/2 L times EMF squared divided by R squared. That is, of course, substituting this into here and making it an infinity. So it is 1/2 times 0.053 Henry for the inductors times 12 volts squared for the EMF squared, divided by the resistance of 0.35 ohms, and we're going to square that. It is 31 joules. That's a final energy stored. Now we're going to tackle this. After how many time constants will half this equilibrium energy be stored in the magnetic field? This is the number of time constants to reach half the equilibrium value of UB infinity. So we know the UB at any point is 1/2 Li squared. So UB then of infinity is 1/2 L. And of course, I at infinity is just E over R. So we substitute that. So UB equals 1/2 L times the quantity E over R squared. Okay, so UB equals 1/2 L at any time is just, we've substituted in for I equals E over R times the 1 minus the exponent of minus T over tau L. We substitute that into here. So UB at any time is 1/2 L times the square of this quantity, E over R, times the quantity 1 minus the exponent of minus T over tau L. We want it equal to 1/2 of what it is at infinity. So it's 1/2 times 1/2 L times the quantity over R squared. That's just this, multiplied by 1/2 to make that. Now at this point, we're ready to do some algebra on this. So we're going to equate these two and solve it for the time. The time will be n times TL. Now n does not have to be an integer. And we solve for time, this equation that we had here, complicated equation, it'll end up being minus the natural log of the quantity, 1 over the square root of 2 times tau L. Okay, so time is n times tau L, and that equals minus the natural log of the quantity, 1 minus 1 over square root of 2 times tau L. And of course, then we can solve that for n by dividing through by tau L. N equals minus the natural log of the quantity, 1 minus 1 over the square root of 2. When we substitute in, at this point we've solved that, n equals 1.2 time constants to reach 1/2 the final energy. Okay, so here's another example. It takes 5 milliseconds for the current in an LR series circuit to build to 90% of its maximum value. What is the time constant of the circuit, and what is the inductance of R equals 200 ohms? This is a charging or building up RL circuit. Time to reach 90% is 0.0050 seconds. And of course, you want to convert everything to SI. I over I max is 90% or 0.90. R equals 200 ohms. L and tau L are to be determined. Okay, we write the equation. I equals I max times 1 minus the exponent minus T over tau L. Tau L is just L over R. And we can solve this, and we wind up with tau L will be minus T divided by the natural log of the quantity, 1 minus I over I max. Plugging in the numbers. Okay, we have a minus sign. We have a T of 5 times 10 minus 3 seconds. That's the time, divided by the natural log of 1 minus 0.90, which is I over I max. It comes out to 2.17 times 10 minus 3 seconds. That is equal L over R. So then we can figure out what L is by just multiplying by that time constant times R. So L equals tau L times R, or 2.17 times 10 minus 3 seconds times 200 ohms times the units conversion equals 0.437 henries. Okay, at this point, we'll do some checkpoints. Circuit A contains a battery, a switch, and a resistor connected in series. Circuit B contains a battery, switch, an inductor, and a resistor connected in series. Initially, the switch is closed in both circuits. How does the behavior of the circuit and current in circuit B compare with that in circuit A, as both switches are opened at the same time? Well, the one that contains the inductor is going to have a time constant. So it's going to take longer to do anything because the inductor is going to fight you every step of the way. The one without the inductor is going to behave almost instantaneously. So circuit B is going to be slower in anything it does. So the correct answer to that is B. The current in circuit B decreases more slowly than that for circuit A since the inductor acts to maintain the current in the circuit. In other words, it retards any change, it fights any change. So it's a decaying exponential. A circuit contains a battery, a switch, an inductor, and a resistor connected in series. Initially, the switch is open. In which one of the following intervals does the energy stored in the inductor have the largest value? Since the switch was initially open, the battery was not in the circuit, so it's going to take a long time for this current to build up. So it'll be a long time after the switch is closed. So the current is built up to its maximum value. So it'll be a very long time after the switch is closed. It'll be 1/2 Li squared. So in other words, it's this kind of curve, and you want this right out here. Okay, as the inductance of an RL circuit increases, the responsiveness, that is how quick it responds to changes, decreases. It gets slower. Because notice in time constant here, it equals L over R. So tau is proportional to L. As L increases, so does the time constant and the time it takes to change. Now notice it's inversely proportional to resistance. So as resistance increases, tau L decreases. Now if you want the maximum tau L, you want the maximum L and the minimum R. If instead you'd want the opposite of that, you want the minimum tau L, you want the minimum L and the maximum R. Thank you.